Okay. Before we get started, any questions on what we went over last time? Because it was really a bit of a handful last time, I thought. We went from force and linear momentum and the familiar Newton's law, second law, and we derived basically from scratch this formula. Here and here, all right? And I was just drawing this before I ran out of time. This is a familiar rigid body. So let me just do a little quickie assessment here. How about it? I need some new people. How about the fellow in the red shirt, looking down with a pencil right there? Yeah, well, he'll look up in a minute. You, sir, in red. What's your name? Jimmy. Once again? Jimmy. Jimmy? Jimmy, what does this formula describe? Tell me the physical concepts. I can read it. I don't need the symbols. Just tell me. I want to know. Well, for example, what's that? What's tau sub b? The sum of torques? Yeah, exactly. And what's the b? I figured that out from the tau. What's the b mean? Exactly. What the first point I want to reinforce is that the torque, like the angular momentum, is defined, like moment of inertia, is defined with respect to a point. You don't choose a point, or you don't state what the point is. You don't know what you're talking about. Okay. How about this gentleman in the blue right here behind, with the coffee cup? What's your name? Renee. Once again? Renee. Once again? Renee. Right. What's this? What's this capital H sub b?
Angular momentum with respect to point B.
Exactly, the angular momentum with respect to point B. And you know as well as I that the angular momentum is kind of the rotational analog of linear momentum, okay? Instead of being in a straight line, instead of being linear, it's somehow rotational and it goes around point B. So you're on a roll here. What's this?
That's the velocity with respect to point B.
Oh, say that again very carefully. What'd you say exact? Say it again carefully. Speak up.
I said the velocity with respect to point B.
Not quite. It's extremely close. How about the gentleman in the blue? New York? What's your name? Jose. Jose.
Which term I was taking?
Oh, yeah, I'm sorry. Yeah. The question on the floor is, what does that symbol refer to?
Well, the velocity of point B.
The velocity of point B. It's not the velocity with respect to point B, it's the velocity of point B. All righty, now, and what's been implied here is that what we've done is that we've chosen a point. We've just, in order to do this, in order to speak of these things, in order to speak of torque and angular momentum and how they're related and so forth, first you got to choose the point around which you're doing the arithmetic, and that's what we're talking about, okay? This is point B, and the V sub B he speaks of is in general, absent any constraints that might be moving. Okay, Jose, what's this?
That's
big P, capital P vector.
the linear momentum of point B. No, wait.
Close.
Of the body?
Yeah, I was with you right up to the last phrase.
Of the body, I would guess.
Exactly. What it is the linear momentum of the, now if you had said, if I had said, this is V sub G. Okay, now, this is, the center of mass has got a velocity. That's what this is. Okay, the linear momentum of the entire body. All right. Jose, here's your chance to get it all back here. What's the difference between this formula and that formula?
In the second formula, V sub B and P are in the same direction, so their cross product is 0.
Oh, very good. Very good. That's an excellent answer to half of the question. Okay? Yeah, no, he's absolutely got it absolutely right. Let me just jump to the punchline here, is that you may get rid of this term right here. You may go from here to here. You may use this when you know this term, this second term is 0, okay? And now here's the subtlety, and I want to make sure I'm saying it just exactly right. Dot, 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 whenever point B, and it turns out there's two conditions, and the two are these. One is when you know that point about which you're going to do all the arithmetic is dead flat 0. That is, you know it's fixed, not moving in inertial space. Its velocity is 0. Everybody see that one there? Okay, unequivocal. That anytime you see a symbol that indicates an object has a fixed axis of rotation, pin joint bolted to the ground, whatever you want to call it, if that point is fixed in space, that absolutely qualifies. You can use this formula with abandon, okay, and confidence that it's right. The other one, and I think, Jose, this is what you were alluding to. Okay? Anytime, some other point, when the velocity of the chosen point V sub B happens to be parallel to what?
Of the ridge, right?
Exactly. When it's parallel to this, then you can get away. Then you're good to go. Then you can use that formula as well. And let me just say, and this is the kind of clarification. Okay, the center of mass that we were speaking of yesterday, this one here is one such point, okay? I think where I went wrong yesterday is I kind of implied that that was the only one, that was the only situation in which you could go this second round. And in fact, as I will show you here momentarily, it's not the only one. There are more than one. All righty? Okay, any questions about that before we go on? Good. All right, here we go. Now, at the end of last lecture, I moved through this very quickly. This is the example of the cylinder. We're in the spring. And what I'd like to do is go through this a little more carefully this time and make a point or two that I think is relevant to this very discussion. So here's our cylinder rolling without slip. Ding, 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 magic term. That's K. Okay, and there's two possible degrees of freedom. Could be X, could be theta. And we're going to say this has a mass M and a moment of inertia C measured with respect to the center of mass. And what I want you to do is find the equation of motion, all right? And you'll be called upon to do this dozens of times in this course. So let me simply say, here are the things that have to be done. This is not necessarily the order, but to me, I don't want to sound like a broken record or just like harping on this, but kinematic constraints are really important, okay? Because you have to understand, you have to be able to spot them, and you have to be able to quantify them with expressions like this. If you don't, you're going to get the wrong answer. You're going to get either, you're going to come away saying this thing's got 2 degrees of freedom, like x and theta, and try and search for 2 equations of motion, or you're going to have one equation and 2 variables in it that you can't straighten out. So the point of the story is you have to, in any, and every problem's different. And let me simply say that the kinematic constraint survives differentiation. So if you know how the positions are related, so too you know how the velocities and the accelerations are related. Also, so you're going to have to do the kinematic constraint. You're also going to have to do a free body diagram, all right? And in this one, this was fairly simple. There's N, there's mg, there is force from the spring, and I'm going to simplify this and call it F sub k, and here is one, I'm just going to, that's the friction force. Let me just see if there's anything else. No, that's it. And you don't really need to be reminded of this, but I put it up here anyway, and I'm also going to put this up here to kind of signify that I'm partial to theta. That's what I'm going for. Okay. Here's a question for you. It's just in passing. Let me see. The lady next to Nico. I'm trying to remember. It's not. I want to say Kathy and Emily and Amelie. I give up. Camille, of course. I was close, right? All right. Very good. Had 2 syllables in it. Okay. What's? I already told you this is Kx. All right. That's the force applied to the cylinder by the spring upon a displacement x. Okay. Again, x and theta are chosen as 0 when there's no loads in the spring. So either a theta or an x displacement creates forces. In this case, the spring goes into compression and opposes the motion. That's great. What's this, Camille? Why did I draw that?
A frictional force?
It's a frictional force. You believe it?
I don't know.
Well, yeah, okay. Nico, why do we need to mess with friction at all?
Well,
She's a little troubled by it, a little uncertain about, you just...
we care about it in the sense that it's non-slip rolling. But
Exactly.
We don't need to know the actual value.
Nicely put. The reason we care about friction is that is the physical mechanism by which non-slip kinematic constraint comes about, okay? If there were no friction, if this were on ice or a frictionless surface, then x and theta could be independent of one another, okay? But when there is friction, there's no slip, x equal r theta, period. All right, Nico, here's what I really want to know. What I think really troubles Camille is the direction of this force. I think when I drew it to the right, she wanted to say, why to the right? Why not to the left? What would you say to such a question?
Well,
A legitimate question.
Yeah, I guess it depends on how we're defining. If the spring is pressing the wheel to the left as drawn on the diagram, then the friction force would be balancing the forces in the x direction, right? No, it isn't.
Let me say that's not the way to do it. Let me just say that is, you absolutely have to go through that kind of reasoning to establish Kx. Okay, you have to go through that reasoning that x is 0, or when x is 0, there's no load in the spring, so when x is positive, the spring is compressed and it opposes the motion. You absolutely have to go through that exercise, but friction is different in an important way that Lauren, I hope, is going to tell us.
Yeah, so friction opposes the motion of one surface against another, and since it's rotating this way, the bottom is going to be moving that with respect to the surface, so friction has to go the other way.
Okay, that sounded a lot like the Nico argument. Yeah, Isabella? Ooh, you're getting close. Isabella says, are we just making this up?
It doesn't really matter, the worst case you find it negative, then you go the other way.
There you go. She said at that time, she says, it doesn't really matter. Okay, and that's the answer. Okay, not to be too flippant about it. We don't know what Camille, we don't, and all this rotate, when this happens, we don't know any of that. Okay, we just know friction's in there. Strategy, pick one. Say that's where it is. We're going to solve for it and eliminate it anyway. Okay, this is an unknown for it. So the direction you choose here is absolutely arbitrary because it's going to go away. Don't worry about it. So unknown force, ditto is true for the normal force and the frictional force, same deal, but not so this, okay? These two are given. There's no, they're different. Okay, not to belabor that point. So let me then do the free body, I'm going to sum forces. Yeah, I'll say apply, trying to dress it up here a little bit. Apply Newton's laws. Okay, let's go in a positive x direction. So what we have here, I'm just going to do this in the interest of time. And what I'm going to do is I'm going to take the liberty of rearranging this to suit me. Okay, now time out. Who's in the back row? The lady in the back row there in purple, what's your name? Katie, can you read that? Did this disappear out of sight? Kind of out of sight. Okay. I can't lift the board, so I'll write it right up here. Okay, that's what that is. Fair enough? Okay, excuse me, okay. That's in the x direction. We could do the y direction, but frankly, we don't care about it. So I'm not going to do that. So here, now we're going to sum torques. Yeah, hang on just a second. Yes, ma'am. Who's speaking?
X double dot.
Oh, I absolutely should. Where did I? This one here? Absolutely. Very good. X double dot it is. Thank you. Okay, so what we're going to do, now we're going to sum torques. We're going to sum moments, okay? Who was the first guy who spoke here together? The guy in the, yeah, can you get his attention? We need you now. We need you now. What was the point you made? Can you remember? We're going to take, we're now ready to sum torques. What should be the first question in your mind? About which point? Absolutely. That's what I was after. Okay? About which point? And let me just say, I'm going to supply the answer because I'm driving up here. I'm going to take point C. So what we're doing here is we're going to sum torques about point C, which is the center of the mass. And I got to tell you, this is a personal preference, and I'll let Professor Vandiver argue with me later, but when in doubt, choose the center of mass, all right? You can never go wrong with the center of mass, okay? There may be other ways that are shorter, that are easier, but you can never go wrong with the center of mass. And me, I'm a simple person, I remember one thing. So I always start with that. You can get more complicated thereafter. Summing torques about the center of mass, because we're going in the positive, the theta, we're going in the clockwise direction because we chose the arrow that way. Spring force doesn't count because it goes through the point in question, no moment arm. Ditto, the weight doesn't count, goes through the point in question, no moment arm. N doesn't count. Only one that does count is F times R, positive or negative. How about the lady on the aisle here? What's your, I should know your name, it's Spanish. What is it? No? Italian? Aviana. I give up. What kind of name is that? She says it's mine. Aviana. Is this first term, is the contribution of the frictional force to the torque about C positive or negative? Good guess. No cigar. Eric? Alex. Yeah, sorry. It's one of those kind of days. Yeah. You agree that's positive? Yeah, wait a minute. Jose, help me out here. I'm looking for a negative, frankly.
It's rotating this way, and
Yeah.
the torque of F is the other way, so it's negative.
You get it? Look at this. And I think, Aviana, you and Alex are thinking right-hand rule, out of the board, all the omega k's have been positive. All that's true. The curveball was, I gave you the big head fake, here, okay, when I said I'm defining theta positive in the clockwise direction, alrighty. And as you can see, F times R is in the direction that opposes theta. So what we have is minus R times F equals I sub C times theta double dot. And it's that simple. And again, in the same spirit, I'd like to rewrite that. Theta double dot plus RF equals 0. Everybody see that? This is a perfectly good, how about is it Kathy in the macro? Can you read that? Good. Okay, now are we done? How about Michael in front row? Are we done? I'm sorry, I interrupted you. I wrote this. Can I just quit? I mean, is this a legit equation of motion? Emma? He seems tentative. No, Emma says no because? Yeah, exactly. First off, where we started this whole conversation, we don't know what F is. All right? We made it up. So we're not done. So, next thing. Okay, eliminate F. That's why I wrote it up there. I can rewrite it right down here. Plus R times F is now mx double dot plus kx, right, equals 0. Hey, we're getting closer. Getting closer. How about it? Next step. Yeah, Emma.
You need to change the x to theta.
Absolutely. And how might we do that? The kinematic constraint. You got it right here, written out in big fat print. X equal R theta. So in kind of one step. Now I do have to be careful here. Let me take my time and go M R theta double dot plus K times R times theta equals 0. And now when I pull these all out, let's see here. Got to take it. Oops, that's not what I wanted. All right. How about it? Emma, you satisfied now?
Don't you have to also the 9 bit of
I'm sorry?
Is it, do you need to simplify it, or?
Actually, no. Okay. Yeah, then we're done. Yeah, that is the point. We are done. What you are looking at, I mean, her point is that I think on the problem set they ask you to reorganize it and isolate theta double dot and so forth, but that's not a requirement. Okay, right here, this is a card-carrying, legitimate, ordinary differential equation. Okay, second order in theta. See the position. Anyway, here's theta and a theta double dot. It's a second order differential equation in theta. All the coefficients are positive. Ooh, that's good. Okay, that'll be useful later. All right, that's it. And let me simply say you could have done it, you could have chosen x instead of this, but this will do. Now, hang on a second. I'm going to draw your attention to this. How about it? Alex, I'm coming your way. I'm going to give you another chance here. Yeah, okay. Same deal, I'm going to apply Newton's laws. This one is the same. This one is unaffected. Only this one, instead of summing about C, now I want to sum about A. Okay, so do it for me, would you?
So you want to sum the torques?
Yeah, that's exactly. I want to sum the torques. And see, I already screwed stuff up because now we got A, now F's gone.
So your only force is going to be the KX.
That's exactly right. The only one is the KX force. And I was going to ask you to do the sign for me. Is it going to be positive or negative? Negative. It's going to be negative, absolutely. So this is what you get. Equals I. And now, what is this? What am I about to write here?
You have to consider that it's, you have to use the parallel axis theorem.
Oh, very good, very good. That's exactly what I really was after here. All I was really after is that now you have to take the moment of inertia about A. All right, so this is right. And in the interest of time here I'm just rewrite. This is simply an inversion of this. And then I want to, let's see here. Theta double dot plus R K times X is R theta. Ooh, look at that. Ooh, we're done already. Is it Sally? I give up. What's your name? Yeah. Elise, of course. Would you concur that we are done here? I mean, it looks to me like we're done. We got a second order equation.
Well, we don't know what IA is.
Excellent. Beckett, she's concerned about our lack of knowledge of I sub A.
Find IA using the parallel axis theorem.
Yeah. So Beckett says, use the parallel axis theorem.
It's the same as the expression over there.
Okay, that's it. All right, that is exactly right. The parallel axis theorem, as you recall, says if you know the moment of inertia about the center of gravity and you wish to find the moment of inertia about some different point A, a distance A away, a distance D away, then the formula looks like that is the parallel axis theorem. And can everybody see that here? Everybody see that here? All right. Now, the reason I dragged you through this is not that, well, I wanted to get a little experience with using the direct method to come up with the equations of motion. But it was really this subtlety. I want to point out a subtlety and something I may have misspoken yesterday. How did, Alex, you got any idea why I chose either C or A as the point about which to take the torques? Well, that's true too, yeah. This is actually where I was, you notice at the critical juncture here, now this is the summation of torques. Okay, notice there's none of that right-hand, or none of that second term present. Alex, how did I get away with that for C?
Well, because C is the center.
C is the center of mass, exactly. Okay? Now, here's the tricky part. How did I get away with it for A?
That velocity of point A is.
Yeah, well, yeah, this is what, I believe I said this yesterday, and I think I was wrong, okay? And I'm looking for Professor Vander to help me out here, but we discussed this in the instructors meeting, and the truth of the matter is, let me talk out of both sides of my mouth with the hope of clarifying and not confusing you further. The A is, in fact, the instantaneous center of rotation, okay? In this instant, at this instant, its velocity is 0, but point A's velocity is not 0. So you might say, well, geez, you can't use it then. But I'm hoping Alex will come back and say, oh, yes, you can. Because point A's velocity is still parallel to that of the center of mass. Fair enough? Kim, you want to add anything to that? Subtle stuff.
Very subtle stuff, and in recitation, we'll take a little harder look at it.
Perfect.